The first presentation for Professor Dr. Miriam Sartor. She is Professor for Environmental Engineering and Technology at College University of Applied Science, Germany. She has more than 15 years of experience in industrial liquid media treatment, filtration and membrane filtration, and material technology. Her research is focused on industrial process water and liquid effluent treatment by hyper process with membrane or biological treatment process. Its presentation titled Ceramic Flat Sheet Membrane Technology for Hyper Filtration Process.
Thank you very much for the introduction. It is my pleasure to be at this conference for the third time and to talk about ceramic membranes. And I hope you all can hear me well. I'm located in Germany and I'm really a fan of ceramic membranes, and it's great for me to see that this time there are so many presentations about ceramic membranes that there is a full session about it. And all this shows me how the conference and even the membrane research group in Egypt are growing. And that is really a pleasure to me. And thank you very much for the invitation. Today, I want to talk a bit about hybrid processes in filtration, in membrane filtration. But the first thing I want to show you is the institute where I'm located at Cologne University of Applied Science, because I think it's also a very interesting location. It's, well, you see it on the picture, or you perhaps don't see it. It is an old landfill, and it is a place for learning about environmental issues, to be trained and to do research while there is active waste management on this site. And we're doing a lot about research on sustainable circular economy, and one part is process water treatment, what I'm doing together with my research group and other colleagues. Today, I want to have a look into ceramic flat sheet membranes with you. This is a little bit the repetition of my last presentations, but stepwise our community in this conference is growing. So I thought I will summarize it and yes, give you a chance to find a point where we can start together to discuss about the hybrid processes we can form and we can develop due to the specific properties of the ceramic flat sheet membranes. And I will show you an example for safe drinking water production with hybrid processes with ceramic flat sheet membranes, and show you some of the perspectives we have in research and development to solve during the next years. Yesterday, we had already several very interesting and, well, comprehensive talks about membranes, and I just want to follow up how to classify membranes when it comes to the ceramic membranes. We learned yesterday already that there are different types of membranes, and one is that the nature shows us how to do it. Cell membranes are important for our life. They have a very tiny thickness of about 8 nanometers and are specialized to very specific transportation tasks. And this is what we try to, well, copy with the technical membranes. Technical membranes are much thicker, although we have the chance to produce thin ones. And they are only dedicated to some tasks. And we have to develop processes and membranes all the time, as we can see what nature is doing, but the copy of nature is quite difficult. What we discussed until now in this conference are more or less all the solid and polymeric membranes, and they are widely used in the field of water treatment, process technology, chemical industry. What is the part of this session today are the inorganic membranes, which are metals and ceramics. And those type of membranes had a significant increase in applications in environmental technology during the last 10 years. Although there have been ceramic membranes before, a lot of things happened during the last 10 years. And here are some papers, it's from newspapers, it's from internet pages, and we see that ceramic membranes are cracking the market. There are high expectations. We have developments which are extremely fast since 2015. There are developments in gas separation, in drinking water treatment, in industrial water treatment. And what we see that the prices become more and more competitive to the polymerics. And this is extremely new, as ceramics were always dedicated to that they are too expensive to be used in broad applications like drinking water. So what I found is this GWI article from 2017, and they are telling us that ceramics are trumping polymerics. They discuss a lot of advantages and disadvantages, and the disadvantages in the past were the costs and the brittleness. The prices are continuously decreasing for ceramic membranes as we have new developments, we have more competitors, and the market is developing very fast. We see that with the high mechanical strength, not the brittleness, but the mechanical strength of the ceramic membranes and even the chemical strength against aggressive cleaning agents, the ceramic membranes allow to develop other types of processes than those which are possible for polymeric membranes. And one of the points was that we have lower membrane surface area per module with ceramic membranes. And when you go into the flat sheet form, the surface area is increased drastically. And this is also a point which allows now stepwise to use ceramic membranes in broader applications. So next point is what we discussed during the last days, that we have different operating modes for pressure-driven membranes. And what I'm talking about are membranes in ceramic form for ultrafiltration and microfiltration. These are porous membranes, and there are different possibilities to install those membranes and to operate them. The classical operating mode for membranes, like we discussed it with the polymerics one, is into-out filtration. This is here on the left-hand side. You have an installation in a closed module housing, and the water is pressed from inside of the module and through the membrane to outside of the housing. And due to the very tiny channels, you have no tolerance to high solid contents. And you often have the problem that there's a filter cake forming inside those channels, and so you have to generate shear forces by cross-flow operation to keep these channels free and to allow this operation of those membranes. And well, this is pressure-driven filtration by high pressures or even medium pressures. Another possibility is on the right-hand side. It's an out-to-in filtration. This means that we filter from outside of the membrane, and the outside contains the active layer where the tiny pores of the membrane are. You have an installation directly in the raw water tank and no limitation to solid concentration, as the dirt stays outside of the membrane. In case you need shear forces to keep the membrane free of the sludge, you can use aeration. This type of membrane is operated by suction pressure. The most common type of those membranes for the submerged systems, the suction filtration, are known from MBR technology. These are polymeric membranes, hollow fiber like the seaweed membranes. But you could also use ceramic flat sheet membranes. And here's a picture of these membranes. And the water, the dirty water, is filtered through the ceramic plate. The separating layer is located on the outside of the membrane, and the retained particles are kept on the outside of the membrane. And the purified water is moving through the inner side of those membranes. So what is the advantage of this type of filtration? You can have a look at the type of filter cake which is formed. And when you go to the pressurized membranes, again on the left-hand side, you compress the cake layer with a high pressure, and stepwise you have a clogging of the membrane and no water is moving through. You have a compaction of the filter cake due to the filtration pressure. And on the other side, when you have a membrane where you work with the submerged systems and you suck the water through the membrane, the filter cake is not compressed, it is more or less fluffy and the water is moving through. And now everything was same for polymerics, but now comes the point only working for ceramic membranes. The high mechanical strength of the flat sheet membranes allow the formation of a filter cake of several millimeters on that membrane without any impairment of the filtration due to the high solid content, as long as this filter cake stays fluffy. And this allows the development of new processes, like hybrid processes with active cake layer. I always put this active in brackets, and you will see it on the next slide, what is happening, why we have active or not active. What we are doing with hybrid process is a direct combination of different unit operations with ceramic flat sheet membrane filtration. Direct combination of different unit operations means that we directly add flocculants, chemicals for precipitation, adsorbents, or ion exchange materials to the feed water, form a filter cake specifically dedicated to the filtration task on the membrane, and then suck the water through the membrane and have a clean filtrate. And here you see such membranes in a module housing, which are covered with activated carbon. The different types of hybrid processes are divided by Serafiltech, a company you may know from the last conferences, and I was working there, and they are a technology provider for ceramic flat sheet membranes. They divide it between cake layer filtration and active cake layer filtration. The cake layer filtration combines the precipitation, oxidation of flocculation processes, supports fouling control, and allows the removal of dissolved and colloidal materials by microfiltration or ultrafiltration due to the combination of the two processes. The active cake layer filtration combines the filtration with adsorption or ion exchange. You see this is a more active material which is on the surface of the membrane, and you see here the power activated carbon and then the membrane. This is a cross section. And this allows the selective removal of dissolved contaminations like ions and trace molecules like PFAS, PCBs, radium, uranium, color and odor. The advantages of these hybrid processes are that you have a compact construction, an efficiency of the the increase of the single unit operation is increased. It is better to combine, for instance, flocculation with a membrane filtration than to have the single process steps separately. You force the pollutants to come in contact with the reaction partner, like the flocculant or adsorbent, by moving and sucking it through the membrane. And you can control the membrane fouling. And this means that these hybrid processes are more than membrane filtration. I will show you an example or two examples from Serafiltech. And I'm very happy that they allowed me to share it, and I'm really grateful to it. Sarah Fittek invented different of these processes for the removal of organic molecules and dissolved ions. And we will have a look on the removal of toxic ions with hydrous manganese oxide, especially now radium. You see here in the picture different types of ceramic membranes here in the cross section with activated carbon, and in this picture below you see that you have a violet color on the membrane, which is normally gray or white, and this violet color is this hydrous manganese oxide, HMO. This HMO process can be used to produce safe drinking water. And the common overview of this active cake layer filtration is shown here in this picture, and it's the same for HMO or for activated carbon. You mix a slurry of your adsorbent in a tank, and then you bring this on the ceramic membrane. This is done for 30 to 60 seconds very quickly, and you have a comparable thin layer of this sludge, this active cake layer on the membrane surface, and then you start the filtration process. And due to these two steps, you have the combination of two processes directly on the membrane. And one example for safe drinking water is from Jordan. The water in the aquifers of the Middle East region contains natural radionuclides, and in Jordan, this radium impairs the groundwater quality and it is suspicious to cause cancer, and therefore it should be removed, and it can be done by reverse osmosis. And this needs a lot of energy. And so when you use the active cake layer formation, you form HMO on the membrane surface, and this HMO is possible to capture the radium nuclides, and they are adsorbed on the HMO. And due to the membrane, the water is forced to move through this layer, and you can produce safe drinking water. This was demonstrated from 2019 to 2021. During the corona crisis, it took a little bit longer for the supply of 2,000 people in a container plant. And last year, a full installation was done in Saudi Arabia at the place of Homaima, and it is an RO pretreatment to remove the radium and to remove even iron and manganese from this groundwater aquifer with a plant capacity of approximately 6,000 cubic meters per hour, a supply for 700,000 people. And this is quite nice and possible due to the combination of different processes. So this is my last slide. The perspectives for R&D are that the contribution of hybrid process of ceramic flat sheet membranes are the chance to improve the removal of hazardous contaminants and trace pollutants from water sources, to supply safe drinking water, and to contribute to closed water cycles. And we even have the chance to recover valuables if we combine the processes in a very intelligent way. And this is R&D, and we have to work on this. Research is necessary to model the mechanisms in the active cake layer, because we have to understand the short reaction times. We have to suppress co-reactions. We have to improve the process design for highest efficiency. And finally, we just have to develop further hybrid processes we cannot imagine today. So these are contact data from me and even the colleagues from Sarah Fittek in case you have any questions. And I go back to this slide because this is important for all our future work, and I thank you for your attention, and I'm open to questions. You can send me an email or even ask now. Thank you.
Thank you, Professor Miriam. I'm pleased to meet you. Any questions?
Yeah, one question. Short question. How often you have to do the backwashing? Very nice job.
For this HMO process, they do the backwashing every 12 to 24 hours. It depends on the loading capacity and on the contamination, but normally it's approximately around 12 hours.
12 hours. And you also have the fouling problems in the surrounding membranes, the fouling issues in surrounding membranes. You can't hear me.
Yeah, I sorry, I didn't get this fully. Perhaps you can just repeat. There's an echo.
You also have frequent fouling problems in ceramic membranes.
Yeah, ceramic membranes have the same problems in fouling, or especially like the polymeric ones, when you have a lot of organic matter in the water. For instance, surface water or some specific industrial water. And when you and the ceramic membranes have the same problems like the polymeric ones. And with these hybrid processes, you can solve those fouling problems. For instance, if you add some flocculant like iron chloride to capture those organic matter, and then you form a fresh filter cake on the layer, and then those fouling problems are solved, and you can very nicely filter the water. And Therapeutic is using this mainly for surface water treatment.
Thank you.
Thank you, Doctor, for the very interesting talk. I would like to ask, you have removed the radioactive isotopes in Jordan, Saudi Arabia, by the active cake layer. What about the total desalination? Excuse me, do you hear me?
Yeah, but you have again to repeat very slowly the question because this echo is incredible.
Okay, sure. I said you have, first, I thank you for the quality of your talk. And I am asking about the possibility of desalination using this active cake on ceramic. You have removed successfully radioactive isotopes in Saudi Arabia and Jordan. What about the total desalination efficiency?
I'm not sure if I got it fully.
Well, I am asking about the total efficiency of your membrane with the active cake layer on the ceramic membrane.
Okay. Okay. Yeah. What when you go to these drinking water applications, you can receive an efficiency of 98 to 99 or higher than 99%. Because you have, depending on the backwash, these 12 or 24-hour backwash cycles, which take approximately around 10 minutes. And then the operating times are very high, and you need comparable less water. So you come up to 99% of efficiency for the drinking water applications. For industrial water treatment, the efficiencies are a little bit lower. It depends on the chemical cleaning you need. But for drinking water applications, you have comparable low chemical cleaning because the water does not affect the membrane very much. I hope this covered your question.
Okay, thank you. Thank you very much.
Thank you, Dr. Miriam.